In the last video, we talked about relations, and in this video, I want to talk about some important properties that relations can have. And this is building up to the idea of something called equivalence relations. So, there's really three properties that I really want to talk about: reflexivity, symmetry, and transitivity. And anti-symmetry shows up a couple of times as well, so we might as well talk about that one too. So, the first thing I want to point out about these properties is that this is indeed a universally quantified thing for all of these. Remember that if you have an if-then statement with some variables involved, it's given that these are universally quantified. Oh, that should be just B, and this is for all A, B, C. So we're thinking about these statements as being universally quantified. Okay, so that means that each of these properties has to hold in every instance. So in order for us to call a relation reflexive, it needs to hold for all elements of our set that each element is related to itself, for example. So let me kind of show you what's going on. We're going to do a really simple example here. So we're going to have a really simple set here. Let's call it A, and let's have it be the elements A, B, C. And we'll have a relation R on A, and I'll do it in digraph form. So I'm just going to put our elements here, and I'll do the relation. We'll call it R, I guess. So each element is related to itself, and each element is related to each other element in both directions. In fact, this is kind of a complete relation. Every possible ordered pair of A cross A is in here. We have AA, BB, CC, ABBA, ACCA, and BCCA. So we have them all. Oh, I think I should have said BCCB here. Sorry. Okay. Well, this relation is reflexive. For every element in our set A, each element is related to itself. So this relation is indeed reflexive. This is also symmetric. So any time that an element is related to another element, the reverse relationship also holds. So you can think of, let's talk about reflexivity for a second again, sorry, just to go backwards a little bit. But you can think of reflexivity as all elements have loops. So each element is related to itself. Here are our loops, right? Look at them. Every element has a loop attached to it, so it's reflexive, sorry. This is symmetric, since all arrows that aren't loops, I should say, are double-sided. So we can see in this diagram, each of these arrows in our digraph are double-sided. A is related to B, therefore B is related to A. This is a symmetric relationship. We'll talk about anti-symmetry in a second. Let me skip that. Transitive basically says anytime that there could be a triangle, there is a triangle. So here, it says if A is related to B and B is related to C, so A, B, C, A is related to B, B is related to C, anytime that there's kind of a path between two elements through another element, there's always a direct path to get there. So because we can go from A to C through B, it means we can just go to C directly. That's what transitivity means. So rather than writing it in words, maybe I'll just say anytime that you have an arrow path like that, so you can go from one element to another through an intermediate element, then the direct path has to be there as well. That's what transitive means. Anti-symmetric, that's a special one. That's a little bit different. Anti-symmetric, well, what does it say? It says that if A is related to B and B is related to A, then it must be that A and B are the same element. So that means there's no situations other than loops where we have double arrows. So maybe I'll write that in. So you can think of anti-symmetry as no arrows are double-sided. So there are 4 properties that we're going to explore. Let's look at an example just to make sure we get the ideas here. In fact, let's do a couple. I think it's good for you guys to pause the video now and make a digraph for this relation on the set 1, 2, 3, 4, 5. Might as well do it for the second one as well. And then looking at the definitions above, determine if the relations are reflexive, symmetric, anti-symmetric, or transitive. They could be any or all of those. So pause the video now, give that a go. Okay, so now that we're back, let's draw our digraph. I'll draw it in a little pentagon-like thing, just so it's as symmetric as possible. So there are elements of A. Let's draw the relation R1 in red here. So we have 1 is related to 1. And just to make sure we know how to write that, we'd write it like this. 1 is related through the relation R1 to itself. 1, R1, 1. We have 2 is related to 2. 3 is related to 3. 4 is related to 4. 5 is related to 5. You can also, if you want, you can think of these as double arrows, of course. Doesn't matter which way you go. It's related to itself. So right now, since we know each element is related to itself, we can say that R1 is indeed reflexive. So let's say R1 is reflexive. We know that just from the first 5 elements of our relation. Let's see the other ones. We have 1 is related to 2. So I'll draw an arrow starting at 1, going to 2. 2 is related to 1. We have 2 is related to 5. 5 is related to 2. We have 5 is related to 3. And 3 is related to 5. Okay. So they're all of the elements of our relation written in digraph form. So is this symmetric? Well, every element here has its mirror image. 1, 2 has 2, 1. 2, 5 has 5, 2. 5, 3 has 3, 5. So this relation is indeed symmetric. R1 is symmetric. What about anti-symmetric? Well, it's not. R1 is not anti-symmetric. And let's do a little counterexample here. Remember, these are all universally quantified, So to prove something wrong, you just have to find one counterexample to it, an existential statement as our counterexample. So does there exist a situation where A is related to B is related to A, but they're not the same elements? Sure. Our counterexample here would be 1, 2, and 2, 1. We found a double arrow, right? That is what anti-symmetry says. There's no double arrows. So we can just say our counterexample here is, let's write it like this instead. Let's say 1 is related to 2, and 2 is related to 1, and I should say under relation R1, but, of course, 1 isn't the same element as 2. So there's our counterexample. Next, we have to decide, is this transitive? Well, let's look at this. We have 1 is related to 2, 2 is related to 5, but we don't have a direct path from 1 to 5. So this is not transitive. So R1 is not transitive. Remember, we just needed to find one situation where it's not transitive, and we just did. So our counterexample here is 1 is related to 2, 2 is related to 5, but 1 is not related to 5. And I should say that this is R1, of course. So this relation here is a reflexive and symmetric relation. Let's look at the next example. Again, if you haven't done this yet, pause the video, try it yourself. Okay, we have, again, 1, 2, 3, 4, 5, R2. Let's do R2 in a different color. How about blue? R2 will be in blue. We have 1 is related to 1, 2 is related to 2, 2 is related to 3, 3 to 4, 4 to 5. So, let's see. This is not reflexive because, for example, 3 isn't related to itself. So we can say, I'll write this in red, R2 is not reflexive, and our counterexample is that 3, for example, is not related to itself. Is it symmetric? Well, no. Again, we have something where we have a relation in one direction, but not in the reverse direction. 2 is related to the 3, but 3 isn't related to 2, so it's not symmetric. R2 is not symmetric. And our counterexample here, there's more than this one. You could do 2, 3, 3, 4, or 4, 5. Any of those will work anytime you have one of those single-sided arrows. So 3 is related to via R2 to 4, let's say, but 4 isn't related to 3. Let me scroll up to make a little more room here. Is this anti-symmetric? And the answer to that is yes, this is anti-symmetric. There is no situation where we have a double-sided arrow, except these loops, right? These loops are kind of double-sided. 2 is related to 2, 2 is related to 2. You can think of these loops. I don't draw them double-sided, but they're the only kind of double-sided loops that we have. So this is indeed anti-symmetric. So R2 is anti-symmetric. Anytime that you have something related to something and the reverse relation, the only time that applies is when both elements are the same. So that's great. It is anti-symmetric. And is it transitive? It is not. R2 is not transitive. And what's our counterexample here? Our counterexample is just the following. Well, we have 2 is related to 2, 2 is related to 3, 3 is related to 4, but 2 isn't related to 4. So we have that intermediate element where we can get from 2 to 4, but we can't get there directly. So our counterexample here is 2 is related to 3, and 3 is related to 4, but 2 is not related to 4. And that's the 4 main properties of relations that I want to talk about. Let's look at a few more things. All right. Now that we know about reflexivity, symmetry, and transitivity, we can start to talk about using these properties. In fact, we like relations that have these 3 properties: reflexivity, symmetry, and transitivity. In fact, if there is a relation where all of these 3 things hold, we say this is an equivalence relation. And again, I talked about this briefly, and we'll see the power of it a little bit going forward. But they're very, very important types of relations in mathematics. There's also something that is important. If we swap out symmetric for anti-symmetric, if we have something that's reflexive, anti-symmetric, and transitive, we call that a partial order. So a partial order you can kind of think of like a less than, greater than type thing, except some elements might not be comparable. And we'll do an example now. We'll start with a partial order. We want to show that this relation, let's say we have a set A and we want to define a relation R on the power set of A. So our relation is going to have elements of PA cross PA in it. And we're going to say that a subset X here is related to a subset Y. So remember, these are subsets of A, or you can think of them as elements of the power set of A. Remember, the power set is the set of all subsets of A. So X is related to Y exactly when X is, and I should have a proper or a non-proper subset here. So X is a subset of Y. So that's the rule for our relation. I want to show that that rule, given a set, indeed gives us a partial order. This relation is reflexive, anti-symmetric, and transitive. So that's what we need to show. Okay, so let's start. So let's do reflexive. Okay, so let's let X be an element of the power set of A, or if you like, a subset of A. Remember, they mean the same thing. We have to ask, is X related to itself? And what does that mean? Remember, our definition for a relation is it a subset? So, is X a subset of itself? Well, of course it is. Every set is a subset of itself. So, yes. So, R is indeed reflexive. Since every element is a subset of itself, every element is related to itself. And by element, I mean an element of the power set of A. So that's great. Perfect. Let's check anti-symmetry now. All right. Remember, anti-symmetry says that for all subsets, say X and Y, if X is related to Y and Y is related to X, then X must equal Y. So let's do that. So let X and Y be elements of the set the relation is on. This is a relation on the set, the power set of A. So these guys are subsets of A. And we want them such that X is related to Y and Y is related to X. So that means X is a subset of Y, because that's what X being related to Y means. X is a subset of Y. And the other one says that Y is a subset of X. Well, this is literally the definition of set equality. Each set is a subset of the other. So, by the definition of set equality, we have that X and Y indeed equal. They have the exact same elements. So, it is indeed anti-symmetric. That's great. And the last one is transitive. So transitivity, remember, it says that if we have three elements of the set that our relation is defined on, and let's call them A, B, and C, I guess. A is related to B, B is related to C, then we must show that A is related to C. So let's do it. So let's call them X, Y, and Z. Let's have them be subsets of A, so they're elements of the power set of A, such that X is related to Y and Y is related to Z. Well, this means that X is a subset of Y, and it means that Y is a subset of Z. And I'll leave it as a little exercise, but I think it's pretty obvious. If something's an element of X, well, then it's an element of Y, and since it's an element of Y, it's also an element of Z. So that means that X is indeed a subset of Z. And I'll leave this just as a small little exercise for you guys to show that. So if X is a subset of Y and Y is a subset of Z, then X is a subset of Z. And if X is a subset of Z, this means, I should say and thus X is related to Z. So we have that this is indeed transitive as well. So we have that this relation, this subset relation, is indeed reflexive. Everything's a subset of itself. Anti-symmetric, the only time an element x is a subset of y and an element y is a subset of x, is when they're the same element, when x equals y. So we have anti-symmetry and we have transitivity. If we have these three subsets of A, so elements of the power set, if x is a subset of y and y is a subset of z, then x is a subset of z. So it's transitive. So it gives us some sort of order. If things are comparable, we can say kind of what one is bigger. So that's pretty cool. So this is an example, indeed, of a partial order. So it's like an equivalence relation, but instead of symmetry, we have anti-symmetry. Now, we'll need this little bit of notation a little bit later, but with equivalence relations, and we're going to do one next, they fall into things called equivalence classes, and that's kind of the key, is this idea of an equivalence class. And basically you pick a representative from the class, and the equivalence class is all elements that are related to that choice that you made. And we just write it like this. You'll see how this works in the following example. This is kind of one of the most important equivalence classes. We're kind of thinking of this dn, in some sense, as a dividing equivalence class. And just to be clear, I want to make n here, so where n is indeed a natural number. Maybe I'll write is a natural number. That's probably better notation. So let's say that n is indeed a natural number. I don't want to get worried about dividing by negatives or dividing by 0 or anything like that. Just for our purposes, we'll just say we're dividing by natural numbers. So we have this relation d sub n for some n, and it's on the integers, so that is the set that our relation is defined over. And we say two integers, a and b, are related, so a dn b, exactly when n is a factor of their difference, of a minus b. And we want to show that this is indeed an equivalence relation. So let's start it off. We'll do one at a time. We need reflexivity, symmetry, and transitivity. So let's do reflexivity first. I'll start it off and I'll get you guys to pause the video and finish it up for me. So remember, we want an element from the set our relation is defined over Z, and we want to show it's related to itself. So let's call it A, B, and Z. Now pause the video and see if you can figure out if A is indeed related to itself and how to show that. Okay, so what do we need to show? We need to show that n is indeed a factor of A minus itself, A, which is the same thing as saying that n is a factor of 0. But everything every integer is a factor of 0, because you can always write n times 0 equals 0. So what does that mean? So it is indeed reflexive. Awesome. Okay, let's do symmetric. We want to show that this is symmetric. So again, let's pick two elements, A and B. And we want to assume that A is related to B, and we want to show if that's the case, then B is related to A. So let A and B be integers, and assume the if part is true, so A is indeed related to B. So this means that n is a factor of A minus B, which means, of course, that I can write A minus B as n times C for some integer C. Remember, that's what it means to have a factor of n. Okay, and we need to show that n is a factor of B minus A. All right, pause the video now. Give this a go. Okay, so that's what we need to show for this to be true. So let's consider it. And we need a way of using our if part here, our assumption. We know A minus B equals n times C. Here I have B minus A, but I can just factor out a negative 1 here. This is the same thing as negative 1 times A minus B. Just switches the signs of both parts of our term there. So, and I know A minus B equals n times C. And of course, I'm going to use associativity and commutativity to write this as n times negative C. And since negative C is an integer, well, I've done it. So since negative C is indeed an integer, I have that n is a factor of B minus A. I wrote it as B minus A equals n times the integer negative C. So symmetry is done. Let me put my smiley face. Let's do transitivity. Okay, so what do we need here? We need three integers, A, B, and C. And now we're going to assume that A is related to B and B is related to C. So this means that n is a factor of A minus B, so I can write A minus B as n times, and I don't want to use C because I already picked C as a variable here, so let's use, let's use R, I guess, n times R. And similarly, since B is related to D, I know B minus C equals n times some integer S, and let's tell people what these are for R and S that are indeed integers. So, again, what do we need to show? We want to write A minus C as n times some integer. So let's consider it. And it looks like I'm running out of space, but I should be able to finish this. It's not a very long argument once you figure out what you need to do. So maybe pause the video now, see if you can figure it out. Remember, we have 2 bits of our hypothesis here. We know something about a minus b, we know it equals n times r, and we know something about b minus c, that equals n times s. So if you can come up with a clever way of writing a minus c in terms of a minus b and b minus c, then you can use our hypothesis here. So think about that, a little hint. Notice we have the a that we want, here's the minus c that we want, here's a minus b, here's a plus b. Okay, now that you're back, well, using that hint that I gave you, well, I can write a minus c as a minus b plus b minus c, and then I'll just bracket it like that. That's fine. So this way I wrote a minus c in a way where I can use my hypothesis. I know a minus b is n times r, and I know b minus c is n times s. So this is n times r plus s, and since r plus s is indeed an integer, we have that n is indeed a factor of what we started with, a minus c. So this is great. We have that this is indeed an equivalence relation. We've proved that this relation is reflexive. We've proved that it's symmetric. We've proved that it's transitive. Now let's talk about equivalence classes. So I want to find all equivalence classes of D4. So like we're dividing by 4. And just remember, we do indeed know what the relation is. It's when n, in this case it would be 4. 4 is a factor of the difference of 2 numbers. Then they're related. They're in the same equivalence class. So let me start a new slide here. We'll talk about this last definition just in a little bit. So let's start with an element in the integers and just see what's in its equivalence class. So let's find the equivalence class of 0. And let me remind you, because it's not on this slide, so the equivalence class of A is all elements x in whatever set your relation is on, such that x is related to A. So it's everything that's related to A. So we want every number that is related to 0. So let's see if we can figure out this set. Let's think about it. Well, we want all numbers, let's call them b, so that 4 is a factor of 0 minus b. So what does that mean? That means that, well, in this case, negative b equals 4 times some integer c. So, well, what numbers are in here? Well, 0 is definitely related to itself. 0 minus 0 is 0, and 4 times 0 is 0. And if we think about it, well, any number that we put in here is going to give us a multiple of 4. So b is just going to be all the multiples of 4. So in the positive direction, 4, 8, 12, 16, 20, 24, etc. And in the negative direction, well, if c equals 1, we get negative 4. When c is 2, we get negative 8. When c is 3, we get negative 12, etc. And it keeps going in the negative direction too. So these are all multiples of 4. So the equivalence class of 0 is all multiples of 4. And just as a little note here, remember, what's an equivalence relation saying? It's saying that each element is related to itself, the relation is symmetric, and transitivity happens. So putting that all together, what that says is that the equivalence class for any element that's in here is going to be the exact same thing. So let's say I picked 8. Well, via the same reasoning as before, because this is an equivalence relation, we have the same set here. 0, 4, 8, 12, whatever. And here we have -4, -8, whatever. And that is, of course, the same as the equivalence class of 0, which is the same as the equivalence class of -4, which is the same as the equivalence class of -352, whatever you like. Anything that's a multiple of 4 is going to have the same equivalence class. All of these guys are in the same equivalence class. Okay, so we got all our multiples of 4. Maybe I'll put this guy kind of in brackets, because this is just really an example to show you something. Maybe I'll even put it in a box. All right, let's do the next element we don't have. We don't have 1. So let's look at the equivalence class of 1. Maybe pause the video, see if you can figure this out. Use that same idea. We need that 4 is a factor of 1 minus b. So think of what numbers satisfy that. Okay, now that we're back, let's do that same idea. So it's everything, so 1 minus b equals 4 times c. And let me rearrange that for b. So this is the same thing as saying that, in fact, maybe we'll solve for -b as 4c plus 1. So it's all integers that can be written as a multiple of 4 plus 1. So, well, 1 can be written as a multiple of 4 plus 1, 0 plus 1. 4 plus 1 is 5. 8 plus 1 is 9. 12 plus 1 is 13. 16 plus 1 is 17. And we can keep going forever. And in the negative direction, we have -4 plus 1 is -3. -8 plus 1 is -7. And that goes on forever. So it's everything that has all numbers with a remainder of 1. When divided by 4, I should say. And you can check. Put any of those guys in there with 1, and you will get that it's divisible by 4. In fact, put any of these two numbers in the relation definition. You'll find they're related because they're divisible by 4. So pause the video now, see if you can figure out the equivalence class for 2 and for 3, and that will cover all of our numbers. Okay, using the same logic, we know that the equivalence class for 2 is every integer that has a remainder of 2 when you divide it by 4. So 2, 6, 10, 14, etc. Here we have -2, -6, -14, etc. So this is a remainder of 2 when divided by 4. And maybe you don't like 2 as your representative for your equivalence class. You could pick any of these guys. The equivalence class of 10 is the same thing as the equivalence class of 2, since by definition of the equivalence class, all of these elements are related to each other. And finally, the equivalence class of 3 is indeed all numbers that have a remainder of 3 when you divide them by 4. And maybe we'll put a couple in here. -1, -5, -9, etc. Again, -1 is -4 plus 3. -5 is -8 plus 3. -9 is -12 plus 3. So you can see these are all having remainder 3 when you divide them by 4. So this has a remainder of 3 when divided by 4. So there are equivalence classes there, and that's how they work. I'll do a few more examples in another video, but hopefully this idea of equivalence classes is starting to make sense to you. Remember, they're made from relations that are equivalence relations, and equivalence relations are reflexive, symmetric, and transitive. So this says, of course, that everything in an equivalence class is related to itself. That's reflexivity. The order that things are in here doesn't matter. That's symmetry. And it says that, well, if 0 is related to 4, 4 is related to 8, for example, 0 is related to 8. And you can use transitivity to show that everything in this equivalence class is indeed related to each other, which is fantastic. So we have these kind of 4 separate sets that, in some sense, partition the integers into equivalence classes. And I don't use that word partition lightly. In fact, we'll show very soon that equivalence relations and equivalence classes and partitions are intricately linked together.